Hello and welcome to the show. Today we're diving into a fascinating area where biology meets engineering, soft robotics. Forget the clunky metal machines you might picture. We're talking about robots made from flexible, squishy materials, inspired by creatures like octopuses or caterpillars. These robots can bend, stretch, and adapt to their surroundings in ways rigid robots simply can't. Now imagine making these soft robots fly, like tiny insect drones. One big challenge is power. Batteries are heavy, and wires limit movement. But what if you could power and control them with light? That's the cutting edge we're exploring today. Light-actuated, soft aerial robots. So how do you make a robot move using light? It comes down to special photoresponsive materials. Think of materials that react when you shine a specific light on them. Two main ways this works: photothermal, where light creates heat, causing the material to expand or contract, like flexing a muscle. The other is photochemical, where light directly changes the material's structure at a molecular level. Liquid crystal elastomers, or LCEs, are popular choices because they deform significantly and controllably under light or heat. Researchers are already making incredible progress. At UCLA, they've developed a tiny flapping actuator called FLAPTOR. It uses light-sensitive LCEs and mimics insect wings, flapping autonomously just by sitting under a constant light source. It flaps up to 13 times a second and generates power comparable to some real flying insects. This is a huge step towards tiny, untethered flying robots powered only by light. Meanwhile, at North Carolina State University, they've created a different kind of aerial soft robot. It looks like a twisted ring made of LCEs. When light hits part of the ring, it contracts, causing the whole thing to roll along a track, like a wire or thread. It's like a tiny, light-powered aerial tram that can carry cargo up to 12 times its own weight, navigate complex paths, climb steep slopes, and even get over obstacles. The potential benefits here are huge. Using light means wireless power and control. No batteries, no tethers. This is key for small, free-flying robots. Soft materials also make them safer if they bump into things, and more resilient. Plus, without traditional motors, they could be much quieter. And we're talking serious miniaturization potential, maybe even down to insect scale. Of course, it's not all smooth sailing or flying. A major hurdle is that current systems often need really intense light sources. How practical is that outside the lab, especially with varying sunlight? Controlling complex movements beyond simple flapping or rolling is another big challenge. We also need these soft materials to be durable enough to withstand flight conditions, UV radiation, temperature changes. And how do you add sensors for navigation without making the robot stiff again? Plus, we need to improve how much force they can generate for carrying heavier loads or operating in tough environments. Despite these challenges, the future looks bright, pun intended. Material science is advancing fast, promising more efficient and tougher light-actuated materials. Combining this with AI could lead to smarter, more autonomous robots. Think about the applications. Tiny drones for monitoring crops or inspecting bridges. Delicate robots for search and rescue in tight spaces. Even explorers for environments like space where remote power is a bonus. So while we might still be a way off from swarms of light-powered robot bees buzzing around, light-actuated soft robotics is opening a really exciting path towards a new generation of autonomous aerial systems, lightweight, flexible, and untethered. Keep an eye on this space. It's definitely one to watch. That's all for today. Thanks for tuning in.